Imagine you're standing on the deck of this colossal cargo ship, right in the dead center of the Pacific Ocean.
Right.
And below your feet, tucked into the dark steel hull, are literally 10,000 tons of perfectly ripe bananas.
That is a lot of bananas.
It is. And if the temperature in that hold rises by even, a few degrees, you lose millions of dollars of cargo in a matter of hours.
Oh, absolutely. It's a disaster.
Total financial disaster. And the only thing standing between you and that disaster is this invisible, relentlessly churning mechanical loop.
Yeah.
And, as someone who loves figuring out how the hidden gears of the world actually turn, you know that a system like that doesn't just happen by magic. It survives because of incredibly precise engineering.
Exactly.
So welcome to today's deep dive. Our mission today is to completely unpack that invisible loop, the refrigeration
That'll
cycle.
be a good one.
Yeah. And to do this, we're pulling from some highly detailed lecture notes. These are from Dr. Sameh Tawfik, who teaches refrigeration and air conditioning, specifically course ME 434T at the College of Maritime Transport and Technology.
Right. So we're looking at maritime scale here.
Exactly. We're going to figure out exactly how engineers manipulate heat on a massive scale. And to help me translate these dense maritime specs into plain English, I'm joined by our resident expert.
It's fantastic to be here.
Hmm.
And, if we're going to dive into this, I really think we need to start by shattering a fundamental myth that most people hold about this entire concept.
Yeah, go ahead.
We need to shift our perspective entirely. The big picture here is that refrigeration isn't actually about, making things cold.
Wait, really? Because it literally feels like it makes things cold.
Right, I know, but scientifically speaking, cold doesn't really exist as an active force.
Mm.
Cold is simply the absence of heat. So this entire deep dive, this whole maritime syllabus we're looking at, it's built around one singular objective, which is moving heat from where it is right now to where we don't want it to be.
Wow, okay.
It's not a cold-making machine. It's a thermal energy transportation system.
I love that. So we aren't creating cold, we're evicting heat.
Exactly. Evicting heat.
We're physically grabbing thermal energy and just throwing it overboard.
Yeah, that's exactly what's happening.
And to pull off that eviction, the engineering specs lay out a framework of four main pillars that make up the cycle, right? You've got the compressor, the condenser, the expansion valve, and the evaporator.
Right.
Think of these as the four vital organs of this mechanical beast.
That's a great way to put it. And the continuous unbroken flow between those four organs is really what makes modern life and especially global shipping possible.
Okay, let's unpack this, because if you want to move heat, you first need a pump to pressurize the system and gather that heat up, and then you need a place to dump it. So that brings us to our first two components. The compressor, which is the muscle, and the condenser, which is the heat dump.
Yep, the muscle and the dump.
Let's start with the muscle. The source materials break compressors down into a bunch of different mechanical types. There's reciprocating, rotary, scroll, centrifugal, and screw.
Lots of options.
Yeah, and I have to admit, looking at all these variations, I'm a bit lost. If they all just pump gas around the system, why do we need so many different types? I mean, it feels like having 5 different types of parts for one single body.
That's a really perceptive way to look at it, actually. To understand why there are so many, we have to remember the context here.
Right, maritime engineering.
Exactly.
Mm-hmm.
This is maritime engineering. You don't use one universal heart because the applications, the scale, and frankly, the maintenance realities out on the ocean vary wildly.
Okay, so how do they differ in practice?
Well, let's contrast two of the mechanisms you just mentioned to see why. Think of a reciprocating compressor. It uses pistons, exactly like a car engine.
Okay, so it's punching up and down.
Right. It violently punches the gas, compressing it stroke by stroke. And that is fantastic for smaller, highly variable cooling loads.
Got it.
But now imagine you need to continuously chill the entire hull of a superfreighter. A punching piston just isn't efficient for that kind of massive, steady volume.
So what do you use instead?
And instead, you'd use a centrifugal compressor.
Which operates completely differently.
Entirely differently. A centrifugal compressor uses a spinning impeller. It looks and acts more like a jet engine, honestly.
Oh, wow.
Yeah, it continuously sucks in and spins this colossal, never-ending stream of gas. You pick the physical mechanism that matches the endurance the specific body needs.
That makes sense.
And it's not just about how they pump, it's about how they're housed.
Yeah.
The syllabus breaks them down into hermetic, open, and semi-hermetic designs.
Right, I saw that. What's the difference there?
So in a hermetic unit, the motor and the compressor are sealed together inside a welded steel shell.
Like perfectly sealed.
totally leak-proof, which is great for zero maintenance. But, and this is the big but, if the motor burns out, the whole thing is trash. You can't open it.
Ah, I see where this is going. If you're on a ship weeks away from port, you can't exactly order a replacement welded shell on Amazon,
Precisely. That is why large ships often use open compressors.
where they aren't sealed together.
Right. The motor and the compressor are two entirely separate units connected by an external drive shaft.
Okay.
So if a motor burns out in the middle of the ocean, the engineering crew can unbolt it and swap in a new motor without ever opening the actual pressurized refrigerant lines.
Oh, so they don't lose all the gas.
Exactly. They don't expose that delicate chemical ecosystem inside the pipes to the salty, humid sea air.
That makes total sense. So the muscle pumps the refrigerant gas, pressurizing it and squeezing all that absorbed heat energy tightly together.
Yes.
But now we have a massive problem. We have this super pressurized, boiling hot gas. But you can't cool a room with hot gas.
No, you definitely cannot.
We have to force this gas back into a liquid so we can use it again. And this brings us to the second organ, the condenser. Its only job is to be a heat dump.
Right. It takes the heat absorbed from the cargo hold, plus the extra heat generated by the compressor's electric motor, and transfers it completely out of the system.
But wait, if the goal is just to cool the gas down, why not just point a massive fan at the pipes? Why involve complex water pumps and evaporators like the diagrams in the notes show?
That's a fair question. The reason is that air alone is terribly inefficient at absorbing heat quickly, especially on the scale of commercial ship.
It's just not dense enough.
Exactly. You need something with more thermal mass. The lecture details three main designs for this: water-cooled, air-cooled, and evaporative condensers.
Okay.
Water-cooled systems use these special copper tubes with massively increased internal and external surface areas to steal heat away rapidly. But the evaporative condenser is where the engineering gets truly brilliant.
Because it's a hybrid, right?
It is a hybrid.
Yeah, looking at the anatomy of the evaporative condenser in the syllabus, there's a lot happening.
There really is.
You've got the hot gas entering this de-superheater coil at the top.
Yep.
And below that, there are spray orifices literally raining water down onto the main coils.
Right.
Meanwhile, a massive ventilator fan is pulling outside air up through the falling water. There's also a water drops trap. Why this specific chaotic setup?
Because it leverages one of the most powerful cooling forces in nature,
Which is?
the latent heat of evaporation. When the hot gas runs through the tubes, the pump sprays fresh water down over them.
Right.
And at the exact same time, that ventilator pulls air up across those wet tubes. So when the water hits the incredibly hot metal, a small portion of it instantly evaporates.
Ah.
And evaporating water absorbs a massive amount of thermal energy from its surroundings.
Just to make that phase change.
Exactly. The phase change from liquid water to vapor
Yeah.
absolutely strips the heat out of the refrigerant inside the tubes.
That's amazing.
It is. The refrigerant condenses into a liquid, the remaining water falls into a trap to be reused, and the hot, moist air is violently exhaled out the top.
You know, next time you're walking past an industrial building and hear a loud, humming metal box, or you stand on a ship's deck and hear that low mechanical roar.
You're hearing this exact heat dumping process.
Yeah. The system is literally exhaling the thermal energy it evicted from inside.
That's a perfect visualization. And that actually brings us to the crucial turning point in the cycle.
Because we've pressurized the gas and dumped the heat.
Right, turning the refrigerant into a high-pressure liquid. But if we want to actually cool the air in our cargo hold, we need to transition from the high-pressure side of the system to the low-pressure side.
We need to let that liquid expand.
Exactly.
Here's where it gets really interesting. We're moving to the second half of our deep dive. The bouncer and the chiller.
The fun part.
This is where the physics turn into what feels like magic, starting with the expansion valve. Dr. Tawfik's notes focus heavily on the thermostatic expansion valve, or the TEV.
Right, the TV.
I love to think of the TV as a strict nightclub bouncer standing at the door of the evaporator.
Right, bouncer.
Yeah. Its sole job is to drop the pressure dramatically and ensure the evaporator gets the exact correct amount of liquid under all possible load conditions. No more, no less.
It's a great analogy, but you have to understand, the stakes for this bouncer are incredibly high.
Oh, so?
Well, the TEV has to guarantee that the refrigerant evaporates entirely before it leaves the chilling coils. It has to create a specific condition known as superheat.
Superheat. Okay, what does that mean?
Superheat means the vapor leaving the evaporator has been heated slightly above its boiling point
Why does the TV care so much about this?
because it ensures absolutely zero liquid makes it back to the compressor.
Right, because liquids don't compress.
Exactly.
If a slug of liquid refrigerant hits those spinning impellers or pumping pistons in the compressor, it's like throwing a wrench into a spinning engine.
It would be catastrophic. The pistons would slam into an incompressible wall, violently destroying the machine.
So it's a bouncer for sure. But how does a purely mechanical valve, I mean, without any electricity or computer chips, know exactly how much liquid to let in to maintain that superheat?
That is the genius of the mechanical TUV. It's essentially a blind bouncer that relies entirely on physical pressure.
How does it sense it?
It uses a small, sealed, temperature-sensing bulb clamped to the exit pipe of the evaporator.
Oh,
Inside that bulb is a tiny charge of its own refrigerant. As the exit pipe gets warmer, meaning the evaporator is starving and the superheat is too high, the fluid inside that little bulb boils.
oh, wow.
Yeah, it expands, travels down a capillary tube, and physically pushes down on a diaphragm.
And that diaphragm opens the valve.
Exactly. That diaphragm pushes against a spring, forcing the valve open to let more liquid in.
That is brilliant. The heat itself provides the physical mechanical force to push the door open.
Yeah.
And then as it cools down, the pressure in the bulb drops, the spring pushes back, and the door closes. It's a self-regulating physical loop.
Exactly. It acts as a proportional controller.
Okay.
But, as the maritime syllabus points out, modern ships are increasingly moving toward the EEV.
The electronic expansion valve.
Right. Instead of relying on boiling fluid and springs, the EEV is controlled by a digital regulator receiving constant temperature and pressure signals.
Much more modern.
Yeah, it uses precise electronic mechanisms, like pulse width modulation or a tiny step motor, to adjust the valve opening. It allows for a level of micro-precision that a mechanical spring simply cannot match.
So our bouncer drops the pressure, letting this perfectly measured amount of low-pressure liquid enter the evaporator. And this is the chiller.
Right.
This is the organ that actually does what we perceive as cooling, absorbing heat from the bananas, the air, or, a water tank.
And the specs provide some really vital numbers here. Saturated refrigerant enters the evaporator at exactly 0 degrees Celsius.
0 degrees.
Right. But it doesn't just instantly make the room 0 degrees. The lecture highlights a metric called the LMTD, or log mean temperature difference.
Okay, LMTD.
Normally, the difference between the cold evaporator and the warmer air being cooled is between 6 to 10 Kelvin.
So LMTD is essentially an engineering grade. It tells us exactly how hard the machine is sweating to bridge the gap between the freezing coil and the warm room.
Precisely. And to bridge that gap efficiently, the heat transfers mainly by conduction.
So the metal has to touch the air.
Yes. The metal of the evaporator must physically touch the medium. That's why evaporators are completely covered in thin metal fins.
To massively increase the heat transfer surface area.
Exactly. The diagrams in Dr. Tawfik's notes show ceiling-mounted versions that rely on natural circulation, where cold, dense air just falls naturally, and then there are forced air versions with massive fans blowing across the fins.
Now, there's a really quirky, almost counterintuitive aha moment hidden in this section of the source material.
Oh, the defrosting.
Yes. It says that to ensure the evaporator keeps its capacity to cool the air, it actually has to be routinely defrosted. Wait, wouldn't a freezing cold, icy coil be exactly what you want to cool a room down?
You would definitely think so. But if we connect this to the physics of the room, the paradox makes perfect sense.
How so?
Remember, the evaporator is absorbing heat from the air. Air naturally contains moisture.
Especially ocean air.
Exactly. When warm, humid ocean air hits a 0 degrees Celsius metal fin, that moisture instantly condenses and freezes. Over time, a thick layer of ice builds up over the entire fin's surface. And here's a kicker. Ice is an insulator.
Wow. So the ice actually creates a thermal blanket over the metal.
Exactly. It completely prevents the heat in the room from reaching the cold metal of the evaporator.
That's wild.
So, paradoxically, if you let your cooling coils get too icy, they entirely stop cooling the room. The system has to periodically pause, melt that ice off, and start again just to remain efficient.
That is fascinating. Okay, so we have the core loop mapped out.
We do.
The compressor pumps the gas, the condenser dumps the heat overboard, the expansion valve strictly meters the pressure drop, and the finned evaporator absorbs the new heat. It's a beautiful, continuous cycle.
It really is elegant.
But in the real world, things aren't perfectly stable. Let's go back to our cargo ship. What happens when that ship sails from the freezing Arctic down to the blazing heat of the tropics?
That's a huge problem for the system.
Right. The system faces massive, sudden shifts in load. If you just had those four core components, the system would either blow its pipes from high pressure or freeze solid. It needs a nervous system.
And that brings us to the final and arguably most complex section of the syllabus: the regulators, protectors, and diagnostics.
The nervous system designed to keep the whole cycle from tearing itself apart under stress.
Precisely.
Let's look at the supporting cast first, the physical system protectors. The text mentions dryers, specifically models DN and DU.
Right, the filters.
Yeah, their job is to filter out tiny metal shavings, dirt, or corrosive acid. They're basically the kidneys of the system.
Good analogy.
And then we have sight glasses. These are models SGI and SGN mounted right into the liquid line.
Those are crucial.
They literally let an engineer look straight into the bloodstream of the machine to observe moisture levels, the oil situation, and how well the liquid is subcooling.
Being able to visually diagnose the flow without actually opening the pipes is vital at sea. The notes also highlight BML shutoff valves placed throughout the lines.
So you can isolate a broken section.
Exactly. You can isolate a single broken section without draining the entire ship's refrigerant. And we can't forget the OUB oil separators.
What do those do?
Well, when a compressor violently pumps gas, a little bit of its lubricating oil always gets carried away in the flow. The oil separator catches that oil from the hot discharge gas and immediately returns it to the compressor crankcase.
So the moving parts don't dry out and seize up.
Exactly.
Okay, here's where I need to push back a bit.
Sure.
When we looked at the expansion valve earlier, we established its entire purpose is to strictly control the flow and pressure entering the evaporator. So why does the syllabus list half a dozen other pressure regulators? I mean, if the TEV is doing its job, aren't all these other valves totally redundant?
What's fascinating here is that they aren't redundant at all.
Really?
At all. The expansion valve is managing the normal operational flow based on temperature. But these other regulators, this absolute alphabet soup of valves that all start with the letter K, they are highly specialized, independent fail-safes.
Oh, so they are for emergencies.
They are the emergency brakes designed to protect very specific organs during abnormal, extreme conditions.
Let's run through them because we have the KVP, the KVL, the KVC, and the KVR.
Yeah.
Let's decode these emergency brakes.
Let's start with the KVP. This is the evaporator pressure regulator. It sits in the suction line after the evaporator.
Okay, so after the chiller.
Right. Its sole job is to prevent the evaporating pressure from dropping below a designated safety line. If the pressure in the evaporator drops too low, the temperature plummets.
And that's bad.
Very bad. If you're chilling water, for example, that water might suddenly freeze solid inside the pipes, expanding and bursting the metal.
Oh, wow.
So the KVP senses that pressure drop and physically chokes the line to keep the pressure and the temperature safely elevated.
So it stops the chiller from freezing itself to death.
Exactly. Next is the KVL, the crankcase pressure regulator. This one is mounted right before the compressor.
Okay.
Think of the KVL as a bodyguard for the compressor motor. Let's go back to your ship full of bananas.
My favorite ship.
Right. So if they just loaded 10,000 tons of hot bananas into the hold, the evaporator is going to absorb a massive amount of heat and boil off a gargantuan tidal wave of gas very quickly.
And all that gas rushes toward the compressor.
Exactly. If it all hits at once, the compressor motor will overload and literally burn out trying to pump it.
Oh, I see.
The KVL senses that incoming tidal wave, pinches the line, and only feeds the compressor exactly the volume of gas it can safely swallow.
Wow. So the KVP protects the evaporator from starving and freezing, and the KVL protects the compressor from gluttony and burning out.
That's a great way to summarize it.
Then there's the KVC, the hot gas bypass regulator. The notes say this injects hot gas directly from the compressor discharge back into the suction line.
Right.
That seems counterproductive. It's basically a false load, right?
Yes, exactly. If the cargo hold is completely cold, but you can't just turn your massive industrial compressor off without causing wear and tear, the KVC feeds it hot gas just to give it something to chew on.
Keeping it running smoothly without overcooling the room.
Correct. It creates an artificial load. And finally, we have the KVR and the NRD, which work together to protect the high pressure side.
The condenser side.
Right. The KVR is the condenser pressure regulator. If our ship sails into the freezing Arctic Ocean, the outside air is so intensely cold that the condenser might actually overperform.
It strips the heat away too fast.
Yes. The pressure could drop so low that the liquid refrigerant no longer has the physical force to push its way through the expansion valve at the other end.
Oh, the flow just stops.
Exactly. So the KVR restricts the flow to artificially keep the pressure high enough to keep the cycle moving, even in sub-zero blizzards.
It's genuinely mind-blowing when you zoom out. And the notes also mention KP pressure controls, which are just hard on-off safety switches that kill the power if ultimate limits are exceeded.
Yep, the final line of defense.
And NRV check valves, which are basically one-way streets that prevent refrigerant from migrating backward when the system shuts down.
Right, preventing backflow.
Going through all this makes me realize something profound about engineering.
What's that?
True engineering isn't just making a machine work perfectly in a pristine laboratory. True engineering is designing all these fail-safes, the KVP, the KVL, the sight glasses, so that the ecosystem survives the chaotic, unpredictable, real world.
That is the essence of reliability. You aren't just building a cooler, you're building a system capable of autonomously defending itself against the environment.
So what does this all mean? If we step back from Dr. Tawfik's syllabus, we see a beautiful, continuous dance of physics.
We really do.
We have the heavy iron muscle of the compressor pressurizing the vapor. We have the condenser exhaling that absorbed heat out into the atmosphere. We have the strict pressure-driven expansion valve dropping the temperature and the finned evaporator quietly stealing the heat from the room.
A perfect loop.
And watching over this entire dance is a brilliantly complex, purely mechanical nervous system of regulators and emergency brakes, ensuring the heart never pumps too hard and the lungs never freeze over.
It's an incredibly delicate high-stakes balance. And, I'd leave you with a final thought to mull over.
Please do.
Since this source material specifically originates from a maritime transport and technology college, imagine the sheer scale of the modern global supply chain relying on this exact cycle.
It's massive.
Think about what happens if a single tiny mechanical component, one NRV check valve, or a mechanical TEV with a rusted spring, fails in the middle of the ocean. The consequences are monumental.
Billions of dollars.
Exactly.
Mm-hmm.
But as we move further into the 21st century, how long will it be before these heavily mechanical components, these pressure-driven springs and temperature bulbs, are entirely replaced by completely digital, AI-driven predictive sensors?
Wow. Yeah.
And when that happens, how will it fundamentally change the very hands-on, wrench-turning maritime engineering principles being taught in classrooms today?
That is a fascinating question to end on. The shift from a mechanic listening to a physical valve click open to an IT tech diagnosing a predictive AI algorithm with a laptop.
It's coming.
A massive paradigm shift for the invisible systems keeping us cool. Well, thank you so much for joining us on this deep dive into the hidden world of thermal engineering. We hope you walk away looking a little more closely at the vents, the mechanical hums, and the hidden machinery running the world around you. Keep learning, keep questioning, and we'll catch you on the next deep dive.